Imagine you are a materials scientist at DARPA in 2012 and your program officer has just handed you a single requirement sheet. One page, one objective. Build a dry adhesive that attaches to any surface instantly, holds a human body under full combat load, releases on command, leaves no residue, works in rain, works on rough stone, works on smooth glass, and does not degrade with repeated use. No chemistry, no suction, no magnets, no consumables of any kind, just the material itself. Village. You know what suction cups do on rough surfaces? They fail. Village. You know what pressure-sensitive tape does after 100 attachment cycles? It dies. Village. You know what magnetic adhesion does on concrete, wood, glass, or biological tissue? Nothing. Village. Every adhesive technology in the history of materials science requires either a specific surface chemistry, a power source, a consumable, or all three. The requirement sheet you are holding describes something that does not exist. Village. The program has a name. Z-Man. The budget is real. Draper Laboratory in Cambridge is primary contractor. Stanford University is on the team. Village. And every engineer in the room knows that the problem, a dry, universal, reversible, self-cleaning adhesive, has never been solved in the entire history of adhesive engineering. Village. Then someone points out that a 50-gram lizard has been solving it for at least 100 million years. Village. On wet bark, on rain-slicked limestone, on smooth glass, at full sprint, in total darkness, without thinking about it once. Village. The question is not whether nature built a better adhesive. The question is how it works at a scale so small that we did not even have instruments sensitive enough to see the mechanism until the year 2000. Village. The surfaces a Gecko actually navigates are not the clean, polished, laboratory-grade glass that adhesive engineers use for benchmarking. They are rain-slicked tropical limestone. Village. They are bark with surface roughness varying across 4 orders of magnitude. They are the underside of a leaf at 90% humidity, coated in a thin film of condensed water. Village. They are vertical concrete walls contaminated with particulate matter, biological debris, and ambient moisture simultaneously. Village. These are exactly the conditions under which every synthetic adhesive we have ever manufactured loses contact. Not degrades, loses contact entirely. This is not a performance gap. It is a categorical failure, and the Gecko does not notice. Village. The design constraints this animal operates under are severe: extreme surface roughness, extreme contamination, extreme and variable humidity. Village. Dynamic loading. The animal accelerates, decelerates, changes direction, inverts entirely, lands from drops, all while maintaining grip on a surface that changes character at every step. Village. And there is one more constraint that rules out almost every engineering solution we would reach for. The adhesive cannot require any time to activate. Geckos run vertically on smooth glass at over 1 meter per second. Village. The attach cycle happens in milliseconds. No mechanism slow enough to require conscious muscle activation is an option. Village. There is an animal that meets every one of these constraints simultaneously. It does not use chemistry. It does not use fluid. Its adhesion is the product of geometry alone. Geometry at a scale so fine it operates at the boundary where classical mechanics dissolves into quantum physics. Village. And it has been operating at that scale for longer than the dinosaurs have been extinct. This is the Tokay Gecko. Gecko. Village. Adults weigh between 150 and 300 grams. The adhesive system built into their toe pads is the most sophisticated dry adhesive identified on this planet, and it is organized at 4 levels simultaneously. Village. Look at the underside of a Gecko toe. You see rows of overlapping scales, approximately 20 rows per toe, running across the pad like the ridges of a fingerprint. Village. These are the lamellae. Each one is sub-millimeter in scale. This is the first level. It tells you almost nothing about where the adhesion actually comes from. Village. Look closer. Each lamella is packed with hair-like fibers called setae. A single toe carries approximately 200,000 of them. Village. Each seta is roughly 100 to 110 micrometers long and 3 to 5 micrometers in diameter. Thinner than a red blood cell is wide. Village. They are made of beta-keratin, the same protein family as bird feathers and reptile scales. Village. As a bulk material, beta-carotene is stiff. A fiber this stiff should not be able to conform to surface roughness, and yet the contact is made. Village. Which means the geometry is doing something the material alone cannot. At the tip of each seta, the fiber splits, not into two branches, into 100 to 1,000 subfibers, village, each terminating in a paddle-shaped structure called a spatula. Each spatula is approximately 200 nanometers wide, 200 billionths of a meter. Village. So small it cannot be resolved with visible light. A standard optical microscope cannot see it. Village. The electron microscope images that first revealed this structure clearly were not published until the year 2000. Village. For all of human history before that year, we were watching geckos climb walls and had no idea what was generating the force. Village. Total CD across all 4 feet, approximately 6.5 million. Total spatulae, approaching 1 billion. Village. Each one of those billion contact points is a quantum mechanical event waiting to be triggered. Village. But to understand what that means and why no one predicted it, you need to understand what happens at the spatula tip when it touches a surface. That is where the physics starts to break every intuition we have. Village. The adhesion produced by the Gecko system is not generated by glue. It is not generated by suction. Village. It is not generated by interlocking with surface features. It is generated by van der Waals forces. Village. The same quantum mechanical phenomenon responsible for gases deviating from ideal behavior, for proteins folding. Village. For molecules adhering to surfaces in a vacuum. Forces that are real, measurable, and arise from nothing more than temporary fluctuations. Village. In the electron clouds of adjacent atoms, inducing synchronized dipole moments in neighboring atoms. Village. Van der Waals forces are extremely short-range. Force drops as the inverse 6th power of separation distance. Village. At 10 nanometers of separation, the force is negligible. At 0.3 nanometers, atomic contact distance, it is the dominant interaction. Village. This is why no flat material, no matter how chemically compatible with a surface, generates meaningful van der Waals adhesion in practice. Real surfaces are rough. Village. Roughness keeps the bulk of the material separated from the substrate by distances of tens to hundreds of nanometers. Van der Waals forces at those distances, essentially zero. Village. The Gecko solved this problem by not solving it at the bulk scale at all. It solved it at the individual spatula scale. Village. Each one 200 nanometers wide, flexible enough to conform to local surface topography independently of every other spatula in the array. Village. Each spatula makes true atomic scale contact with a small patch of surface. The van der Waals force across that patch is tiny. Village. Multiply it by 1 billion spatulae in simultaneous contact, and the total force is 20 newtons. Village. Enough to support the animal's entire body weight on 2 front feet with margin to spare. Village. A single seta, measured directly by a MEMS force sensor in Keller Autumn and Robert Fultz Laboratory at UC Berkeley in the year 2000. Village. Produced a maximum adhesive force of 194 micronewtons under optimal preloading. Village. The mathematics of contact splitting predicts that dividing one large contact into n smaller contacts multiplies adhesive force by the square root of n for the same total area. Village. The Gecko splits its contact into roughly 1 billion subcontacts. The adhesive performance follows the theory exactly. Village. And the theory, before the Gecko demonstrated it was physically achievable, was considered a mathematical curiosity, not an engineering target. Village. But raw adhesive force is not the part of this system that stops you. The part that stops you is what happens the instant the Gecko needs to let go. Village. Detachment is instant. It requires no energy, no muscle activation. Village. The Gecko simply hyperextends its toe, peels the CD back at a steeper angle, and the entire adhesive array releases in a single wave. Village. The force required to peel a spatula off a surface at a steep angle is approximately 2,000 times lower than the force required to pull it straight off. Village. The Gecko uses angle to switch between maximum adhesion and zero adhesion. Attach by dragging. Release by peeling. No chemistry. No switching mechanism, no power consumption, pure geometry controlling quantum mechanics. Village. Consider what reversibility requires in every human adhesive system: a solvent to dissolve the bond, a UV light source to trigger photochemical release. Village. A temperature change to melt a thermoplastic, a mechanical actuator to retract a suction cup. Village. Every reversal mechanism we have built requires energy and time and adds mechanical complexity. The Gecko reverses adhesion by changing the angle of its toe by approximately 90 degrees. Village. The energy cost is indistinguishable from walking. The time cost is the duration of a single step. Now add the self-cleaning requirement. Village. If you coat a gecko's feet in fine silicon carbide particles, abrasive grit that should clog the spatulae and destroy contact quality. Village. The animal regains full adhesive performance after approximately 4 steps on a clean surface. Village. The particles transfer preferentially to the substrate rather than staying on the CD because the substrate offers more total contact points to a particle than the CD can. Village. The self-cleaning is passive. It requires no wiping, no rinsing, no energy. It is an emergent property of the geometry. Village. Now compare this to where we stand. The most advanced synthetic Gecko-inspired adhesive demonstrated at human scale, the PDMS micro-edge array developed at Stanford University under the DARPA Z-Man program. Village. Operates at a feature size of 40 micrometers. Village. The biological spatula is 200 nanometers. That is a 200-fold difference in critical dimension. On smooth glass, in controlled laboratory conditions, the Stanford system works. A 99-kilogram climber carrying a 22.7-kilogram pack climbed 7.6 meters of flat vertical glass in 2014. Village. That is a real result and an extraordinary engineering achievement. Village. On rough concrete, the surface a gecko climbs every day, the synthetic system fails. Village. The 40-micrometer wedges cannot conform to surface roughness at the length scales that dominate real-world surfaces. Village. The gecko's 200-nanometer spatulae can. The gap between the two is not a matter of effort or funding. It is a matter of fabrication and of a physical principle we still cannot reproduce at the scale that makes it work. Village. But this is where the engineering gap stops being the most interesting problem. Because when researchers try to understand why the spatula size is 200 nanometers specifically, Village, and not 20 nanometers, and not 2 micrometers, they found something that rewrote a foundational assumption of materials science. And that answer is in the physics. Village. At the visible level, what you can measure with a force gauge and examine with a microscope, the mechanism looks almost straightforward. A flexible fiber makes contact with a surface. Van der Waals forces act across the contact area. Force is generated. Remove the contact, force disappears. This was the entire explanation until approximately 2003. Then researchers began asking a question nobody had formally posed. Why 200 nanometers? Is the spatula size arbitrary, or is it optimized for something specific? The answer required building a precise mechanical model of what happens when a nanoscale fiber contacts a real rough surface. Real surfaces, even surfaces that look smooth to the eye, have roughness features at multiple length scales simultaneously. A polished glass surface has nanoscale roughness from the polishing process. A limestone wall has roughness from micrometers to millimeters. The gecko adheres to both. The question is which roughness scale matters most for van der Waals contact. The answer, confirmed in 2022, is that roughness wavelengths below approximately 70 nanometers dominate gecko attachment. The dominant roughness limiting contact on real surfaces is sub 100 nanometer. A spatula 200 nanometers wide can conform to roughness features at approximately that scale. It is geometrically comparable to the roughness it needs to bridge. A spatula 2 micrometers wide sits on top of the asperities and achieves almost no true molecular contact. The 200 nanometer spatula size is not a biological accident. It is the engineering optimum for maximizing van der Waals contact area on the class of surfaces geckos actually encounter. Evolution arrived at the theoretically correct feature size for the operating environment. Through natural selection operating across millions of generations of geckos falling off walls. With no knowledge of contact mechanics, no instruments to measure surface roughness, and no theory of van der Waals forces. Nature ran no finite element models, published no papers on contact mechanics, and still arrived at the answer that took human materials scientists until 2022 to formally confirm. But go one level deeper, and the geometry becomes more sophisticated still. A CETA made of uniform beta-keratin, stiff at every point from base to tip, would be mechanically suboptimal. The base needs to resist buckling under shear load. The tip needs to be compliant enough to conform to nanoscale surface roughness. These requirements are in direct opposition. A stiff fiber resists buckling but cannot conform. A soft fiber conforms but collapses. Standard engineering resolves this with composite structures. A stiff core and a soft outer layer bonded together. The Gecko does something more elegant. A study in 2021 confirmed that individual Gecko CETA are functionally graded materials. Young's modulus decreases continuously from base to tip, with up to a 20-fold difference in magnitude across the length of a single CETA. The fiber gets progressively softer toward the spatula end, not in discrete steps, but continuously, following a smooth gradient determined by the local molecular architecture of the beta-keratin. The analogy is a fishing rod, a rod that tapers from thick and rigid at the handle to thin and flexible at the tip, transmits force efficiently while allowing the tip to bend and conform. A rod of uniform stiffness either transmits force poorly or breaks at the tip under load. The Gecko CETA uses the same gradient principle, achieved through a protein structure that varies its crystalline fraction from base to tip. This is the finding with the most direct engineering consequence. Every synthetic Gecko-inspired adhesive built to date, PDMS microwedges, polyurethane fiber arrays, is fabricated from a single material of uniform stiffness. They make a trade-off the biological system does not, compliant for good contact, in which case they buckle under load, or stiff for load resistance, in which case they cannot conform. The biological CETA makes neither compromise. Fabricating a synthetic fiber with a continuously graded stiffness profile across 100 micrometers of length is not currently achievable with commercial manufacturing processes. Electrospinning can vary fiber diameter, but not material composition. Now add the problem that no one has solved: wet surfaces. Van der Waals forces collapse to near zero when a water layer of even 20 nanometers separates two surfaces. Every synthetic adhesive fails in wet conditions. The Gecko does not. Laboratory measurements show that Tokay geckos maintain adhesive performance on wet hydrophobic substrates, and in some conditions improve it. Two competing hypotheses exist. First, at high humidity, beta-keratin absorbs water and softens. The softer spatulae conform more intimately to the surface, increasing real contact area and partially compensating for the water layer effect. Second, thin water films on hydrophobic surfaces may contribute a small capillary adhesion component that supplements the van der Waals force. Both hypotheses have experimental support. Neither fully explains the data. A 2022 review in the journal Friction cataloged the outstanding questions directly. These are not rhetorical questions. They are open problems with dozens of active research groups working on them. And there is one more layer, the deepest one. The entire hierarchical architecture of the Gecko toe, lamellae, setae, branches, spatulae. Every level has been studied individually. Every level contributes measurable adhesive enhancement. But the total adhesive performance of a complete Gecko toe is not accurately predicted by summing the contributions from each level independently. The system performs better than the sum of its parts. We can measure the output. We cannot fully model the system that produces it. And until we can model it, we cannot engineer it. Step back from the spatulae. Step back from the van der Waals forces and the graded stiffness and the billion simultaneous contact points. Consider what the Gecko actually represents as an engineering object. It is the existence proof of something the entire field of adhesive engineering spent most of the 20th century implicitly assuming was impossible. A dry, substrate universal, reversible, self-cleaning, energy-passive adhesive that operates across 4 orders of magnitude of surface roughness. In wet and dry conditions simultaneously, at high cyclic frequency, without degradation, from a single biological material. No chemistry, no power, no consumable, geometry, and quantum mechanics, organized at nanometer precision across an area of 200 square millimeters. If we fully crack the fabrication problem, if we can manufacture synthetic CD with both the correct nanoscale geometry and the correct graded stiffness profile simultaneously, the downstream applications are not incremental improvements to existing technology. They are categorical changes to what is possible. A universal surgical adhesive that bonds to wet biological tissue, holds under physiological loading, and releases cleanly on command, would eliminate sutures and staples from large classes of surgical procedures. It would enable wound closure in field medicine without specialized equipment. It would allow implantable devices to attach to organ surfaces without mechanical fasteners that damage tissue. Jeffrey Karp's group at Brigham and Women's Hospital at Harvard Medical School has already demonstrated early-generation Gecko-inspired tissue adhesives. The gap between those prototypes and a clinical product is the same gap as in the materials science: nanoscale fabrication precision on a biologically compatible material. In space, where surfaces are clean and conditions are predictable, the Gecko gripper already works. Aaron Parnas's team at NASA's Jet Propulsion Laboratory tested their gripper on the International Space Station in 2016, successfully grappling a 300-kilogram floating robot. For space debris capture and satellite servicing, the partial solution is already operational. The full solution, one that works on any surface in any environment, remains ahead of us. On Earth, the limiting problem is what it has always been since 2000: rough surfaces. Wet rough surfaces, contaminated rough surfaces. The bark, the stone, the wet concrete that the Gecko navigates, and every synthetic system fails on. The feature size required to match the Gecko's performance on those surfaces, 200 nanometers, conforming to sub-70 nanometer roughness wavelengths, is below the reliable manufacturing threshold of every scalable fabrication process currently in commercial production. The question that remains genuinely open is this: is the wet surface adhesion of the Gecko a consequence of the van der Waals mechanism, a consequence of capillary forces, or a consequence of the graded material properties changing spatula contact behavior in humid conditions? Or some coupled interaction of all three that only emerges from the complete hierarchical system functioning together? That question has been actively studied since at least 2005. It remains unresolved in 2025. The Gecko did not design its spatulae. It did not know about van der Waals forces, or contact mechanics, or graded stiffness optimization. Natural selection ran the experiment across millions of generations of animals that needed to climb and chose, through attrition, the architecture that worked best across the widest range of surfaces. It arrived at a solution so precisely tuned to the physics of its operating environment that 25 years of research has produced a partial reproduction that works on smooth glass, but fails on the surfaces the original has navigated since the Cretaceous. Without incident since the Cretaceous. Somewhere on a tropical limestone wall tonight, a Tokay Gecko is running at a meter per second across a rain-wet surface that would defeat every dry adhesive we have manufactured. 1 billion spatulae in simultaneous contact. Van der Waals forces operating at atomic distances across 1 billion independent contact points. Graded stiffness adjusting compliance from base to tip in a fiber thinner than a red blood cell. The whole system attaching, self-cleaning, and detaching in the time between footfalls, passively, effortlessly, without a single calculation. The next investigation in this series turns to a different adhesion problem entirely, one that operates not on solid surfaces, but at the interface between two liquids, in conditions so chemically hostile that no synthetic material survives contact. That one is next.